So let's study what you see. Here you see the symbol of the OPA 211, and beyond it, under it, is the macro model for this operational amplifier. And it's not a small one. You see, there are even MOS transistors in it and bipolar transistors in it, and it's really large. And I thought I tried it once in the free edition of this simulator, which is limited in number of nodes, and then it was too large for the simulator. Here you see the amplifier. This is I did not connect the capacitors for biasing because I'm just only interested in the small signal performance and the step response, and I connected this point to a 2.5 volt supply, so it is halfway, and it would be the same as if I did it according to the diagram, but this gives a cleaner simulation because you don't have the settling time of your biasing first. So here is the uncompensated amplifier, this one. And here you see the same amplifier with the micro model, and you see it is compensated. I both have the phantom zero at the output and the phantom zero here in the feedback network. So this is the TI model uncompensated and the TI model compensated. And here you see a Laplace block that is has this expression that is also in SliCap for the gain. So it has the poles and the zeros as I have defined them also in SliCap. Here you see the output impedance of the operational amplifier, and for the rest the circuit is the same. And here you have the input capacitances of the operational amplifier, just as I did in SliCap. And here is the compensated circuit. So here you have the phantom zero compensation, 2.2p and 727 ohm. And here you have the same without simulation. And now the question is, what does it show? Is it reliable if you compare it to the measurements? Because the measurements is Mother Nature, and Mother Nature is always right. So you see, this is really a fast simulator. And the model, the blue one, so let's put some legend in it. So the blue one is my model, uncompensated. That's exactly what SliCap also told us, this peaking. And you see in the TI model, uncompensated, I don't see any peaking, not at all. So, but in the measurements, we have seen the peaking. We have seen the ringing of the step response. And these are my model compensated is this one. And the TI model compensated is the green one. Now let's look at the step responses. Here you see my model uncompensated, and you see the ringing, as was predicted also by SliCap, and it was a little bit less in the measurements, but it was there in the measurements. We have seen the ringing in the measurements. And here you see in the TI model, there is not at all a TI model uncompensated. The red one, there's a little bit like overshoot, but it really looks like Butterworth. Only a few percent overshoot this red one, and for the rest a nice plot. So although the macro model is really very large and provided by the manufacturer, I think we learned a lot that modeling of the operational amplifier, just only the behavioral aspects that are relevant. But here you see, we did it in SliCap, gives really very much, and from the data sheet, give a much better result than using this macro model, and it is much faster. Now here you didn't see how slow it was, but let's say it is really, if you have more operational amplifiers and these huge models, it can really even makes conversion, generate convergence problems or make the thing really very slow.